So just to start off with, this is going to be pretty different from the other talks. So I come from the world of e-commerce and IT conferences, where people like pace from one side to the other and seem like they're really, really knowledgeable and say things quite slowly so that it seems like they've been thinking about it for a long, long time. So that is going to be my style. Unfortunately, that's the way that I've had to speak to fit in the business community in the past, so that they don't really figure out that I'm, a huge nerd. But I think that you guys are going to like it. I think it's going to be a lot of fun at 4 p.m. And I have some interesting Easter eggs in here. So I kind of hope that everybody just feels like they're in a class with their favorite professor and they're super excited and ask whatever you want, and just have a good time, man. So, all right, so what's my story? My name is Eduardo Siman. I don't even know my name. So I go by Eddie usually. I was born in Miami, 1982. When I was 10 years old, Hurricane Andrew destroyed the houses of pretty much everybody I knew. Nobody died, which was great. And I didn't have school for a month, which was amazing. But basically,
hurricane days.
Yeah, hurricane days, So when that happened, experiencing Hurricane Andrew was basically what made me obsessed with hurricanes. It sounded like this train that would just not stop and just get louder and louder and louder. The house heard it was just shaking, and I was like, this is so cool, best ride ever. So that's when I became super obsessed with hurricanes. Unfortunately, life took me in a different direction. I was a math undergrad, and then I ended up going into SAP consulting. So if you guys know, SAP is a software that's used by really big companies. So I did that for a long time. Then I went to get an MBA because that's what you do when you're a consultant. So I went to Columbia, I got my MBA. It was great at Columbia because there's a lot of math there. So I did a lot of mathematical finance classes. And then I spent 11 years as an IT director. I don't even know how where the time went. But basically I was oh my God, this corporate life is terrible. I need to do something else. So I was you know what? I'm going to start my own company. So in 2022, I started Worldsphere, and the idea was we're going to figure out hurricanes somehow with AI. We're going to figure it out. So no problem, right? Super simple. Okay, so we're going to get to a lot more stuff related to Worldsphere. But first, here's the first Easter egg. While we've been drinking coffee, AI has been diligently analyzing everything we've said. So before my presentation on image-to-image models, let's see what AI thinks are the highlights of our first 2 days. So how do we structure this? How can we do this so we can make sure that we're not doing some crazy stuff? Well, one is, and this is going to apply to the image-to-image, I promise, maybe. So to avoid hallucinations, we're only going to get direct quotes from YouTube transcripts. Now, okay, YouTube transcripts might be wrong. They might not be exact. I've looked at YouTube transcripts of my talks, and sometimes it's a complete mess. But that's what we have to work with, right? And then, right at the end, we're going to let the AI kind of, give us some suggestions, what it thinks we should do, as a group. What would the AI do? So the intent here was to basically show, how far we've come with agents. And what I did was I used Claude Opus 4.5, which I think is the best model out there, in my opinion. And I used it using various agents doing different things. And they put together this information. I did not touch it or modify it. All I did was tell them how to change it. And let's see. And then my presentation will come, I promise. OK, so here we go. Here's our workshop summary for the first 2 days as per Claude Opus 4.5 agents. So, and by the way, if I'm talking about your talk and you think this is not a good quote, just let me know. So we started with Kathy, talking about foundation models for medium range forecasting. So Claude thinks that the really important stuff that Kathy talked about was that pre-trained machine learning models that have to encapsulate a huge amount of potential downstream applications, and so they're really hard to build in a way where you can fine-tune them for everything that you need to do later on. So I'm paraphrasing the exact quote that Claude is getting, because I didn't want Claude to think on its own. So one of the things that it got, which I thought was totally an important part of the talk, was majority of the uncertainty of our climate models comes from the representation or misrepresentation of subgrid variability of aerosol cloud interactions, which is true. We know that cloud parametrization, cloud microphysics, and understanding kind of aerosol forcing on climate models is something that is not easy, right? So it goes on to talk about GenCast outperforming other models, then kind of saying like, look, none of the AI models can predict like important diagnostics like precipitation. And I think that this is relevant because ERA5 doesn't have good precipitation, so we all kind of have to deal with that. And I like this quote. It said, adopting foundation models for science requires some quality assurance, and you see a lot of these models coming out in publication, but not necessarily quantitative evaluation with respect to operational systems. So I think that captured what Kathy said pretty well, and I think it's true. Like we have so much great research, but where's it going into operations, right? Why does it take so long to go into operations? Okay. I'm gonna try not to go so slow because I do have my presentation. This is the secret presentation. Okay, so TOMS. So basically, you can frame AI for weather as an initial condition problem, right? You have an initial state, and you move it along mathematically to the next state. Climate, it's a boundary condition problem, so different kind of partial differential equation. But they both have a huge challenge, which is the out of distribution challenge, right? So this is pretty good for Claude. Like, I would say like that's a pretty good choice. And I thought this one was good too. Oh, by the way, these are the timestamps, just the timestamps of when the person said it as per YouTube. So at 34 minutes of his talk, he said climate models, if well-designed, should be able to give you the response to many different imagined counterfactual trajectories, which makes me think of geoengineering and what would happen if like one country just started putting a ton of did stratospheric aerosol injection and things like that. And I think, yeah, I don't know that much about climate models, but yeah, they should be able to predict that, right? So Professor Gill talking about kind of the grand unification of climate theory between nonlinear deterministic Lorentz and linear stochastic Hasselmann. Like, I don't really know what that means, but I think it's kind of okay. I think this one was something that, when he said it, really stuck out to me. And Claude picked it up, which was, I think that they're not going to solve all our problems. I don't even think they have asked any interesting questions. That really surprised me that he said that. But he said, maybe there'll be emulators for database enhancements. Interesting that somebody kind of who invented like so many aspects of like signal processing in the climate world has kind of this view like, I'm not so sure what AI is going to do for us. Johan, very cool mathematical presentation about algebra and symmetry. And I think that probably the AI did not do such an amazing job on this one. Maybe the last one is a good one, which is like you can find any group, any symmetry you can think about as a physicist or engineer and say, how should I think about my invariance? So you can reduce the need for data because more symmetry means you need less data. And that's kind of a good concept, easy to understand. I think that because this was like so mathematical, Claude was like kind of lost. It was like, so he's like, we now have a rotation invariant bispectrum on the sphere. Like, I think we know what that is because we were at the talk, right? But like that outside of context really wouldn't make much sense. Okay, so the next talks, a lot of talks about cloud microphysics, and I think that the job that AI did here was actually pretty good because it picked up like some of the biggest problems, and some of the comments that I picked up were summary comments that I think the author or the person giving the talk would have actually picked out. But in general, there isn't like a consistent ability to pick out the best quotes. Obviously, I constricted it. I constrained it massively by saying you have to use quotes. With Professor Schneider, I think it did a better job. Like, for example, it picked out like, look, there's no AI model that can do the basic thing that Manabe did in 1965, which predict the response to increase in CO2. I thought that was a very important thing that he said, and it picked that out. With Damien, this was like the most important thing he said at 6 minutes, and it picked it up. So I give it an A+ for that. And by the way, that's probably, I think, my favorite thing in the conference so far, that line. With Dimitri's, I think it actually did a pretty good job there, because projecting quantum observables is an automatically positivity-preserving operation. From a mathematical point of view, I thought this was probably the most important thing he said. Now, in terms of what are we doing here, I think that this was important. One typically looks at two types of operators. The first is a composition operator, which is known as a Koopman operator. So it's kind of like saying, okay, here's like a basic explanation, and then here's something that's giving you kind of the final piece, right? And if you notice, it chooses a lot of stuff like right at the beginning, and then a lot of stuff right at the end. So it's like here at 33 minutes, where he said like replacing everything by their quantum mechanical counterparts, rather is like using probability densities, where you have an evolution of density operators. That was like once he was kind of summarizing. So it seems to kind of get the beginning and the end, put them together. So I'm almost done, I promise. I will get to my actual presentation. For Adam, which was like a very philosophical talk that had like a lot of like meaty, like, back and forth. And I was wondering like, what's it gonna pick up? And I think that it kind of failed a little bit, because it picked up things like, for example, I'd say physics is not always interpretable. The word emergence comes up often. Like that really on its own was not like the heart of the talk. Maybe things like this, saying deterministic models are learning this, trying to approximate conditional expectations. But like I really liked this talk, and I thought that it was, a way to think about things completely differently. And I don't think it really was able to do that. Maybe the last one, which is, and this, I think it kind of is cheating. It's like probably getting the last one, like the last thing that the person said. So physics is difficult, the climate is a complex system, but climate models are complex themselves, right? So some points for that. Okay, so is somebody timing me? Or do I have infinite time? So I told Claude, like, what should we do, right? Like, now you're allowed to think. So I put here like editorial content, right? This is synthesis and not direct speaker quotes. And I'm not gonna go over this in detail, but it'll be available for you guys to look at later. And I'm really interested to hear what people think about these pathways that Claude came up with. Okay, so back to hurricanes. So that was probably kind of an unexpected non sequitur, but I just felt like I absolutely had to do it, because agents are just getting so absolutely crazy these days. So why do we actually care about hurricanes? First of all, hurricanes kill a lot of people. So you might think that hurricanes only kill like 42 people, like the number of people that died in Hurricane Andrew. But that's what happens in the developed world. Hurricanes can kill 200,000 people in Bangladesh and Myanmar. They're just called cyclones, right? They're not called hurricanes. Hurricanes are really bad in terms of the number of people that they can kill. So the problem actually is a problem related to saving lives. It's not just a problem related to like, oh, are we gonna like have our skyscrapers destroyed? Like, no, hundreds of thousands of lives per year are at stake. And we need to figure out how to predict these things, right? Like, this is an actual moral imperative. Anything that Michael talked about, I'm gonna try not to talk about too much, because he knows it way better than me. But I will just kind of mention that, there are various areas. So like the World Meteorological Organization has a mandate that every single cyclone has to be tracked, right? And because of that, over time, we've had satellites that can give us images at 10, 15-minute intervals, right? Like GOES-18 or Himawari for Japan. There was subjective analysis, which I think Michael showed beautifully, which is basically this idea, the Dvorak technique, that you can just look at the structure of brightness temperature and be like, oh, here's what the wind is. And that's kind of like the motivation behind the methods that we use at Worldsphere. Okay, some kind of important things to know before you look at what we're trying to do, just because like they're a little counterintuitive. So like this tiny hurricane is the same as this one, except a few days before. It was a Cat 5 right there, and it was a Cat 1 here, okay? This is the wind field. Typically the hurricane center will show 34 knots, 50 knots, and 64 knots. So that's what the colors mean. So you could see the wind field was really, really, really small. Maximum, the wind field for the highest winds. And also even the 34, 50, 64 was pretty small as well. And then it like quadrupled while it underwent extratropical transition, which is what happens when you get into the mid-latitude. So just keep in mind, like, size of the storm is really important. That's why trying to diagnose the wind field is important. But not just because we want to try to figure out where the maximum wind is, but we want to know, what does this thing actually look like, right? Okay, so here's like the huge problem. And this affects Michael as well as me and anybody working in hurricanes. Wind data for hurricanes sucks. I don't know, can I say sucks? It's really bad, okay? Why is that? Well, first of all, hurricanes spend most of their time over ocean, right? We barely have enough ocean buoys, even in the developing world, let alone in underdeveloped countries. I mean, the ocean is just not very well measured, right? Atmosphere is barely measured, but way better than the ocean. So it used to be that ships would like go into these storms and be like, oh, what's going on? They don't do that anymore because they know that it's a storm, right? So like we don't get those kinds of measurements from ships. We do have two really cool things. One is called a scatterometer. So this is polar orbiting, so it's like lower, closer to the Earth, and it's got radar. Somebody asked about this before, right? So it's got radar, 12 to 24-hour return times. You could see the swath is not going to necessarily give you the information that you need. I mean, only 3/4 of the wind field is shown in that, and honestly, that's a really good one. This is like probably the best we have. This is called synthetic aperture radar. Amazing resolution, but this is my issue with it. SAR, what it's looking at is the roughness of the ocean, right? So it's like, okay, I'm looking at one variable, which is how are these waves moving? How high are they? Okay, great. So I know that because I'm SAR, and SAR is cool, synthetic aperture radar. I'm this really cool instrument. But then I have to try to decide what is the wind speed. And I read this book on SAR, and they were like, yeah, so we just like multiply by 0.7. I was like, what? You just multiply by 0.7? And it's like trying to look for better and better ways of getting that raw data and turning it into wind speed, and just continually disappointed. But I still think this is probably the best ground truth that we have. Unfortunately, we get really small swaths, and we barely get them. So we're not in a fantastic situation when it comes to that. How much time do I have, by the way? 30, okay, I'm going faster than I realized. That's good. We'll have good questions. It'll be fun. Okay, so what have people tried to do that I think is noteworthy that you guys should know about? First, John Naff and his group have done amazing work related to trying to get different types of signals and putting them into one wind field picture. So they get infrared, they get microwave, because we have microwave on satellites as well, and scatterometer data. And basically you're getting all these different frequencies across the radiation spectrum, and based on that, kind of saying, this is what I think I'm seeing, right? So the first thing we did 3 years ago when the company started, and when I first started working with my co-founders and my colleagues, which I forgot to mention, I'm so sorry. So when I first started talking with Dr. Nolan, Professor Nolan at the University of Miami, and Sarah Ollier, who for the last 3 years we've been working together on this, and now Brian McNulty, who's a fantastic meteorologist, has been helping us as well with the data. But when Professor Nolan and I started talking about this, he thought, because he knew John quite well, and he said, this is going to be a great training data set. We got it. We had to compile it in Fortran and get F90, F70, and like all these files. Like it was crazy. It was like 4 all-nighters. And when we finally put it into like real usable information, it was way too sparse. There's just not enough info. So it's like, it looks pretty here, but not every one of these is a data point, right? Which is going back to something that Michael was talking about, like hurricane data is really sparse, right? Even when you have a hurricane hunter, you're not going to have every single data in every single part of the hurricane. You're just not. So, I think it's important to say, like, there's been really good progress on using AI for all kinds of things related to tropical cyclones, right? So I really like this paper by Wang and Li in 2023, which is Deep Learning Tropical Cyclone Radius. So what they do is they take a combination of brightness, temperature, infrared images. It goes 18, channel 13 for those who care, and then they take the quadrants and they put each of those into a neural network, like relatively simple neural network that has a fully connected layer at the end, and they have a transformer and a tension layer, and boom, they get an output. Issue with that, it's not an issue. I mean, it's just why it's not enough is that it gives you the radius of 34, 50, and 64 knot winds. Okay, that's fine, but what we really want is the whole wind field. Okay, so what is our method? And R being Worldsphere, which I'll define kind of in this case as me, Professor Nolan, Sarah Ollier, and Brian McNulty. What's our method? What have we been working on? So we do wind field generation directly from infrared. All you need is a picture. You don't need anything else. You just need a picture. And the original idea was that computer vision is incredibly well developed and has amazing neural networks, right? This company started in 2022. 2017 is when the Transformers paper was written. It's also when the GAN was basically, came to life, right? 3 years after 2014 when we had XGBoost, which by the way, it still outperforms tons of neural networks. But my thinking was like, computer vision is like really good. Why don't we use it for hurricanes, right? Like we should just think of these things as images, as videos. And so that's what we did. And so what I'm going to present to you here is one of our methods, like the least secret, right? Because there's secret ones that I can't tell you about. So one of our methods, which is generative adversarial networks, which you kind of very nicely teed up for us. Thank you. This is what we get. Very high spatial resolution, 3 by 3 kilometers, which is really good. Temporal resolution, 10 to 15. I probably should say this depends on whether the satellites are like working as they should, right? Every once in a while, like you don't get that image after 10 minutes and you have to wait like another 3 or 4, or you might get a bad image, even from GOES 18, or even from Himawari, like these amazing, like super well maintained satellites that are relatively young, right? They are not perfect, right? But still, we rely on them, and we can rely on them to a certain degree. It's not like we're like using a pure function, right? Because we can't use functions, or we can't have ways of interpreting satellite data that are independent of whether the satellite's going to degrade over time. But it's the best that we have, right? So we've used both synthetic, so we've talked a lot about that, and real data sets to train. And our goal is size and shape of the wind field. So it's not necessarily just intensity. I mean, intensity obviously is part of this, but we want to get the whole wind field. We want every single aspect of it, right? Like everything. We want to know every single little thing about the 10-meter wind. Okay. So I'm going to talk about like the models that we've done, but I don't want to get like too into the specifics. You guys can ask me questions. I want to just talk more about why it's cool. So this one we call our wharf-to-wharf model, which is because it's trained on weather research and forecasting simulations. Why is that cool? It's cool because the National Hurricane Center, when they try to figure out if they're going to put some new instrument out there, like, for example, what Michael was talking about, which is that drone that went into like the boundary layer. How do they figure out like if it's going to be a good instrument? The way they do it is they use these nature runs. What's a nature run? A nature run is basically like a reanalysis of a particular set of hurricanes using the WRF model. And putting in all the information that we know actually happened, right? So it's like we have the simulation, and then we put in what actually happened. We get basically like the best possible, like, this is the reality of what we had, right? So this is why we think that this is a really good training set. It's not the only one that we use. We think it's a good one, right? So one of the things that we do is we basically get the brightness temperature. Synthetic, obviously, it's from a simulation. So let's just put ourselves in simulation land. We're in WRF land right now. This is not real data. We have a simulation. It's real in the sense that it's being informed by real hurricanes, but it's not real in the sense that it's coming from satellite. We have brightness, temperature, and we have wind field. And what we do is you put the brightness temperature in and you get the wind field. It's pretty simple, and it's kind of cool. Okay, what's the second one that we have, or that we really like? So this one, we learn about the merge IR dataset. It's a great dataset, it's well maintained, it has tons of hurricanes in it. Michael Fisher talked about it. And what we did was we got the merge IR dataset, and Brian McNulty was the one who helped us with this, and we couldn't have done it without him. Because he knows like so much about hurricanes, which it's insane. We got the merge IR data set, and we got the brightness temperature from merge IR. So this is real. This is like legit real. And then we got the parametrization that NHC uses. So like it's not real in a sense, but it's like about as close to reality as you can get, right? So this is basically the way the National Hurricane Center looks at the wind field, right? So we train from the real, which we call the mirror or merge IR dataset, to para, which is a parametric wind field that's used in operations. So kind of back to a comment that Kathy made that the AI picked up on, where's the operational part of this, right? We're really trying to like be as close to operations as possible and talk to the folks at NHC so that eventually we have something they can use. I mean, we all know that it probably would have to be in Fortran, right? Because that's what they do, is everything is in Fortran. But I think we're going to forget about that for now and just like figure it out later. Okay. What is the reason why we use image to image? Like why? That like nobody else does that, like in weather and climate AI, at least as far as I know. Everybody gets gridded data sets, and they get those data sets, and then they get variables, let's say Z500, precipitation, humidity, latitude, longitude, and they say, okay, let's put this into a tensor. Great, so we'll put it into a tensor that fits into a neural network. And that neural network was actually expecting to see red, green, blue, and then channel. So like, what are you doing, dude? Why are you putting like humidity, temperature, wind into a model that was built for RGB? Like, how do you think that's going to work out? Amazingly, it's actually worked out pretty well, but I don't think it's a good idea. I don't think it's sustainable. And also, why not use everything that computer vision has to offer? So we tried a whole bunch of stuff, and we finally settled on image-to-image translation. So the idea here, for those of you who hadn't heard of this, is basically doing a style transfer. So imagine that you have a painting like the Mona Lisa, and you said, I want to see what this painting would look like if Picasso had made it. So that's the one on the left. If Van Gogh had made it, the one in the middle, and Monet on the one on the right. So the underlying structure stays the same, but the style is transferred. So these methods have been used even before like AI was like a famous thing, right? Like you can get computer vision papers from like 20 years ago, and they were doing style transfer. They just weren't doing it with neural networks, right? So, okay. Yes?
What's special about RGB and neural networks? I mean,
nothing is special about neural networks per se in RGB. What's special is the neural networks that were built for images or for videos. Because they were like, everything about that network was made to be optimized for that specific input data. That's, in my opinion, what's special about it. Might not be true. I mean, this is my hypothesis, right? We'll see. Okay, so in the same way that you can get basically painter A's painting and apply this style transfer operator to make it look like it was painted by painter B and still conserve the core of the painting, what you can do is you can get something like satellite measurement or LiDAR or radar, and you can turn that into something that you can't see, right? A variable that is not easily observed. And when I say turn, I don't mean like literally derive it like from first principles, but you can create a function that matches them, right? And there are many ways to do that. Like at a very basic level, you have, a set of probabilities A, a set of probabilities B. You want to link them together. There's so many different ways that you can do that, right? We've talked about diffusion. You have flow matching, which is like a kind of controlled diffusion. Another way to do that is generative adversarial networks. So that's what we do. Okay. What is a generative adversarial network? Why is it good? So at a really high level, we like this because it's really critical and it never gives up. So a GAN is basically like the worst teacher you ever had that gave you an F on everything until you had it perfect, right? So the generator will try to create what it thinks is a real wind field, right? It only knows what the brightness temperature looks like. It knows nothing except brightness temperature. So imagine you're a painter, whatever, and you get a bunch of brightness temperature, wind field, brightness temperature, wind field, brightness, okay, so you see a bunch of those. And then I give you a new brightness temperature, and I'm like, what's the wind field? Unfortunately, your teacher, who hates you, is going to say, that's a really bad wind field, go take it back and try again. And that's going to happen over and over and over and over and over until finally the teacher, which is the discriminator, will say, I like it. Good, this is going into my set of real wind fields. And that's how it starts to learn what's real, what's not real. That's basically how GANs work as per me. Those of you who know them better, please correct me. You gotta have kittens in every presentation, right? Come on. Like, how do you not put a cat in a computer vision presentation? I'm sure you guys are thinking, well, computer vision, you rotate things. Like, wouldn't that just mess everything up? Yes, correct. For 2 years, we got that wrong. And we finally figured out you should not rotate things. It changes the physics. Don't do that. But we still use data augmentation because it gives us more data. I mean, we're starting with sometimes fake, some synthetic, sometimes real data, but we don't have a lot of data, right? We have in the order of 1,000 to 5,000. What we really need is hundreds of thousands or millions. If you look at the big data sets that were used for computer vision, CFAR, right? Or, like these are gigantic tens of millions of images. We don't have that. So we have to at least try to create a little bit more. So we do that. So for example, we'll do like a random crop. So like a small little piece of the wind field will just be like deleted. So like this occlusion here with this cat. Or we'll do a blur, right? We won't do rotation, but we'll make things brighter. So increase the intensity of either RG or B. And what this does is it gives some flexibility to the model. I mean, this is pretty simple stuff. Data augmentation is like super classic stuff, but it's important because like if you're doing computer vision and you do rotation on hurricanes, you're gonna mess up.
Eddie,
yes.
Why does rotation change the physics?
It changes the interpretation of the physics that the discriminator has because it starts to think that you're looking at a southern hemisphere cyclone. I'm not talking about rotation this way. I'm talking about like flipping along a 45-degree angle. Yeah. So, all right. So the model. There's two important things that you need to know about this. One is that neural networks are like way easier than you think they are. Everybody tries to make it seem like neural networks are so ridiculously impossible, but they're not. Like you have this image that has 256 by 256 pixels. That's it, right? And then it's got 3 channels, red, green, blue. Recently, we've added the latitude and the maximum velocity, but we don't need that. In fact, it hasn't really helped much. Okay, you put that in here, and then it just starts to like literally make it coarser and coarser and coarser until you get this. Then you have a latent space, which is probabilistic space, no longer image space. So you've sort of gone from pixel space to this probabilistic latent space, but then you have to go from the latent space and build something new. How do you do that? Because you have weights that you've learned through backpropagation. You've learned these weights, you understand these weights, you know now what's correct. The discriminator has told you what's correct. So now, as a generator, you start building this thing, and eventually, you get to something that looks good. From the so we use something called PatchGAN. I mean, we've tried everything, but PatchGAN has worked relatively well for us. From From the discriminator's point of view, it's getting both images, right, combined. So it sees, here's the brightness temperature, and here's the wind field that this dude, the generator, thought was good. And then here's latitude, and here's Vmax. And let me figure out if this is good or not. So basically, it'll say like true, fake. So in this case, it looked at it, and it was like, no, 0, not real. So it doesn't do like a binary analysis. It does a pixel-wise analysis, which is why all our error metrics, or most of them, are pixel-wise RMSE. So we use, to the best of our ability, a combination of computer vision metrics, like pixel-wise RMSE, as well as meteorological loss, or meteorological metrics that make sense, although sometimes it can be a little bit difficult because the two kind of areas don't necessarily coincide. I'm not going to talk too much about the model pipeline. I think not super important. The parameters, I don't think there's anything super interesting here. Basically, we use Atom as an optimizer. Everybody does. On the learning rate side, we do cosine annealing learning rates, where we basically go from 0.0001 to 0.000001, depending on the cosine annealing function. Sometimes we also have like a feedback learning rate, where basically like based on how the loss is going, we will change the learning rate. I gotta tell you, like, this stuff is not always like science. A lot of it is just kind of messing around. Like sometimes we've done like 200 epochs, and like the loss just doesn't get better. And so we're like, all right, like why don't we just change L1 to 100? You know, L1 being like one of the parameters of the loss function. We did that once, and suddenly we started getting like a more blurred image, but in some cases, a better result. I mean, there's so much tinkering that goes along with this. So this is basically our two models working on the images of real hurricanes every 6 hours. And you could see what the result is as a hurricane strengthens. On the top is Larry, 2021. On the bottom is Lee, 2023. Obviously, we chose very strong hurricanes, because if not, you can't see the full life cycle. It's important to note, the ground truth is, as I explained, in this model, the parametric view of what really happened as per NHC in the hurricane community. In this model, it's the synthetic wind field that the weather and research forecasting would give you, right? That model would give you. Generated is the image that our GAN makes. So this is the closest thing we know to truth, and you can argue with me with that, and a lot of arguments would be really good. Oh, yes?
Why does the WRF-to-WRF have some like static features in the background that don't seem to be changing?
With which one particularly?
Bottom right.
So here?
Yeah, it seems like there's like patterns in the sort of along the edges that don't change.
Yes, that's a really good observation. So what we've seen is that when you start training, the model learns kind of like the inner core of the wind field really, really well. I mean, if it's a tropical storm, it's not going to do a good job. And then as you get trained more and more and more and more, it starts to understand rain bands. And then after like 30 hours of training, it starts to understand the size of the wind field. But this edge over here, which is basically like no wind or beginning of wind field, it struggles with. And that's when we do our RMSE, pixel-wise, this is where we have a lot of problems. So that's really good that you pointed it out. Like, that's like super good. Here are the results. I think yes. Is time over? I have no idea.
We have a question from
The robot.
Oh, David. Oh. Or who? David.
Can you hear us? Can you speak up?
Yeah. One question I had related to this, for your decoder, are you using pixel shuffle for the decoding? We found some issues with patch artifacts in our Wexformer model when using just regular conv transpose, and pixel shuffle seemed to fix a lot of those.
That's a really good point. We do not use pixel shuffle. In fact, we've made some changes to the batch normalization layers that I didn't put in here, but maybe I was embarrassed to admit that we were messing around with something that's like usually so standard, but yeah, we don't use that. I remember because I remember the day that I took it out. But yeah, we've made some changes to normalization layers. We've tried all the different activation functions, ReLU, GILU, cell, everything you can imagine, hyperbolic activation functions. And we kind of just go with what works. But that's a great question. I mean, like hyperparameter training, like the space of hyperparameters that could be optimized for this is massive. Like we haven't even started to, get to the beginning of the wind field. I'm not going to say a digging analogy because it's not relevant. Yes.
I just wanted to share for the image edge challenges. In fact, with DJ, I worked on a project where it was an image model and it was thunderstorm classification. So it's like a few years ago, but doing like a deep dive into the analysis. Most of the error cases were when the feature of interest was towards the edge of the image, and so some of the suggestions were sort of just silly, like cutting out and I'm sure there's more sophisticated ways to deal with it, but it wasn't even like a generative issue. This was just traditional image.
So when you're really just using images as opposed to basically like using like the meteorological data, when you're just using pixels in the neural network, you do have issues with boundaries. And within like the whole history of computer vision, like a lot of the work that's been done has to do with trying to fix boundary problems. Before AI was popular. I think, to be honest, that the way that we're going to get to a solution here is looking at computer vision from the 80s, from the 90s, from 2005, 2010, before AI was popular, and trying to use all those different methods, because they worked. They worked for doing computer vision back then, and I think we just haven't had the time to explore it. That's kind of my hypothesis of what might be helpful. But it's always going to be a problem. Boundary issues, literally there's no way to get rid of it altogether. I've thought of making these circles, right? Or maybe doing some kind of cyclical adjustment, right? Like putting in some kind of cyclical adjustment to the loss function or something like that. I don't know how to solve that. That's super hard. Other questions?
Yeah, so word-to-word seems to give something that looks more realistic than mirror-to-para, which to me is not realistic at all.
It's not supposed to be.
Yeah. Now, have you looked into whether the simulated IR and the wind speed relationship in WRF is sensitive to the choice of parametrization schemes?
We have not. In fact, we've had the same. Oh, am I going forward? I was trying to go backwards. We've had the same parametrization scheme for WRF for everything, as in the Cloud-to-Null in 2019. That's a great question. I mean, the opportunities there are massive. I mean, like, you being an expert on WRF, like knowing how to host it in the cloud and make all those changes, like, we haven't even gotten started with what we could do and what we could try to, what we can try to mess around with.
Yeah, just be aware that there's a bias in there that's intrinsic to the physics that are chosen.
Yeah. Yeah. I'm going forward, backwards. I'm losing myself. Yes?
Yeah, a couple things. So the features that I think was Marcus talked about earlier at the edges that seem to be static, I wonder if you just keep training. Like I've found that when I'm just looking at simple functions, I see that the training starts to nail the stuff that contributes to most of the cost function, early on, and I have to go really long. Like I have a collaborator who used to, early on in our work together, he would think that it was stalled, and I would say, just keep running.
Yeah.
I don't know if you're running on your own, hardware, or if you're having to pay per hour.
We use. Sorry to I apologize to NVIDIA folks, but we use Lambda Labs, and we use the H100s on Lambda Labs. Typically 2 to 3 at most.
So you're paying for the time, I guess, basically.
When we want to do like 5,000 images and want to do it for like 30 hours, yeah, well, it'll cost us like $100.
Yeah. So okay. So then what I was going to propose, I guess, isn't going to be feasible. But like let's say if you're on your own hardware,
yeah,
you get to 30 hours and you think this thing is converged, I would say take that model, go off and use it, do whatever you want to do with it, but just for kicks, let it keep running in the background.
Yeah.
And you'll probably start to find that some of those, some of the things that were being pointed out at the edges, it'll start to converge. It's just it took a lot longer because it wasn't contributing enough to the cost function.
That's a really good point. If you did it on a Google Colab L4 on like a Colab Pro account, you probably could have that thing running for like 10 days.
Yeah.
But an A100 would cost you maybe $30, but on an L4 you'd pay maybe $4.
Yeah.
That's a great idea. I'm going to do that.
The other thing you mentioned earlier, that something wasn't a pure function because you have to take into account the fact that the satellite, the radar data,
Correct.
Gets worse over time. So, I guess to a large extent, functional purity is about like what are you exposed in your argument list, right? So that might just be an argument for including time as one of your arguments, right?
Right, because T equals 1970 is a very different satellite than T equals 2026. Yeah. That makes a lot of sense. I hadn't thought of it so broadly. You have 5 questions, or I have 5 minutes?
Whichever you want.
All right, any more questions, or should I keep going? Okay. Okay, so I think it's important to like talk about when the stuff you do does not work. Like, I guess, we're a company. I guess in like the corporate world, people wouldn't do that, but we're just like a small startup. So like, we want people to know what doesn't work. So what tends to not work? When the hurricane is like just starting to form that dense central overcast and the vortex is aligning and the guys at the National Hurricane Center are trying to figure out if it should get a name, it doesn't do so great. Not surprising, like that is the area where so many people are doing research, right? Because it's like, is it gonna be a hurricane? Is it not gonna be a hurricane? It tends to overestimate what the wind field is when it's just kind of starting to become like maybe a Cat 1 from a tropical storm. You see here, red is when we think that when we're saying that our prediction is giving a different number, right? So no, actually, I apologize. This is distance in nautical miles. Blue would mean that we're giving a higher number, and red would mean that we're giving a lower number in terms of the distance in nautical miles. If I flip that, then just do the inverse. This one. So again, it's important to admit, like, what doesn't work? Well, if you guys know, there's something called eye wall replacement cycles, right? So that's kind of hard for this model because when the eye is expanding and kind of disappearing and another eye is forming outside of it, it's kind of hard for the model to know which is the real eye, right? And that actually is something that is hard for hurricane researchers to know. We don't really necessarily know when the vortex has like become the outer vortex versus the initial inner vortex. Michael Fisher can explain that to you. So it struggles. Like, look, this is red. Like, ground truth was you still have this kind of tiny, very tight vortex. We thought, or our model thought, eye wall replacement cycle happened, so we got it wrong. So, okay, how do we fix that, right? Like, how do we make it better? Like, the whole point is actually to get to some operational method, and that's why we did the parametric stuff. So Brian McNulty told us, like, what you're doing, the NHC cannot use. And some folks at the NHC told us also, like, we need to see it in a parametric format to put it into the rest of the workflow. So, like, what is the point of this if we can't get it to be used and actually try to save lives, right? Probably not going to be in the US, probably going to be in Bangladesh or Myanmar or somewhere else. But like I said, it's a moral imperative. Like, this is serious stuff. A lot of people don't realize. Okay, our results, they're pretty good, but they're not the absolute best, okay? They're pretty close to being the absolute best. And we've really worked very, very hard on trying to get to state of the art compared to every single other method. And we're very, very close, but we're not there yet. But we are very close, a lot closer than we were 3 years ago. So you guys can look at this later on, but essentially we do a root mean square error on a pixel-wise distribution. In contrast to what Michael Fisher found, which is super interesting, we have a lot less error on strong hurricanes. For his model, he's trying to find the center of the hurricane. So it makes sense that having that multi-step process would lead to more error with stronger hurricanes. In our process, we won't try to find the center, right? We're just like, dude, here's an image. So what are the images that are the most symmetric? So there was a question about axis symmetric nature of hurricanes. And when a hurricane becomes fully axis symmetric, when it's intensifying, when it can go into rapid intensification, guess what? That's really easy to recognize, right? It's just like this circle with another circle inside it. Like from a computer vision point of view, it's two concentric circles. So we're at the point where we're comparable to best tracked data. So we think, based on our conversations with other researchers in the National Hurricane Center, that if we continue working on this, it will be something that can become operational. And I think that things have changed in the way that NHC adopts products. Like you see with the Google model. It was like they didn't do the 3-year validation period that every single other model had to go through. They just were like, oh, this is working. Let's just kind of start talking about it, right? So in one of the Hurricane Melissa discussions, which Milan was showing what the discussions are before, National Hurricane Center said, the Google DeepMind model is predicting this. That's not the way they used to operate. So we think that that's why, as a company, we can actually get somewhere. Super boring. Basically, we have pretty good results, but not the absolute best. We looked around and looked at what everybody else had done, and there's some good stuff out there. Not using the same method, of course, but we're just looking at trying to derive a wind field from just having a brightness temperature. Last things that we've been doing is we've been trying short-term prognosis, 3 hours, 6 hours, just to see, okay, can we do more than just diagnose? So far we're getting promising results. I wouldn't say that this is like groundbreaking. I'm not going to say like this is the most amazing thing ever, but I was kind of surprised that when we were doing 3 hour, 6 hour predictions, our error didn't just like totally blow up. That being said, I think that as we continue to do this kind of work, we're going to find that with developing cyclones, with tropical storms, we're going to have a hard time. That's it. So I think I ran out of time. Basically, what are the takeaways? We can successfully generate realistic tropical cyclone wind fields from just an image. It costs a few bucks. It's super fast. Takes about 10 seconds, maybe 3. And what do we want to do? We've been working on diffusion, flow matching, transformers, vision transformers, everything you can imagine. The results are not good enough to be presentable yet, but we work on all that stuff. Prognosis, multiple time steps, putting in multiple time steps instead of just one. And then obviously operational deployment, that's what we want to do. Like that is our goal, and we hope that we can get there eventually. And that's it. Any questions?